Okay, so for the first kind of EAS that we're going to consider is halogenation. So a couple questions that Klein has suggested we consider before we begin, and I agree. Do you think an aromatic ring is more likely to act as a nucleophile or an electrophile? Why? So recall, please, that the question that we're always asking in organic chemistry is, where's the nucleophile, or what of all the lines and dots and letters that you see, which one is the most likely to act as a nucleophile, and which one is most likely to act as an electrophile, right? And then, bam, right? And so you go, let's go back to red. And we've answered the question. That's it. That's what organic chemistry is. So, look at a benzene ring, an aromatic ring, and tell me, is this more likely to act as a nucleophile or an electrophile, and why? Right? So it's obviously now it's important. We don't have formal charges. We don't have lone pairs of electrons, right? So it's a little subtle. It's not simple. You have to look at that and say, what am I looking at when I look at a benzene ring? And it's important, I think, to appreciate that what you're looking at is a pancake of pi electrons above and below the plane. There's a pancake of pi electrons here. Okay? And so it turns out that it is most likely to act as a nucleophile. All right? Do you think bromine, molecular bromine, is more likely to act as a nucleophile or an electrophile? Why? So this is a difficult question. I don't think this one's as easy, right? Because you're used to seeing a nucleophile that looks like that, right? So when I tell you that we have this, because it's molecular bromine, you surely you're tempted to go, oh look, it's got a lone pair of electrons here. I bet you that's going to attack somebody. And it turns out that's not what's happening here. It didn't happen in chapter, I don't remember now. Is it chapter 8 where we did addition reactions? So in addition reactions, we had bromine. It's very important. Very important. Bam. Right? Wow. Yes, that's exactly what happened. And it bothered us at the time. Because at the time, again, you're used to looking at bromide as a nucleophile, yes. But bromine as a nucleophile, no. And it's a big difference. I mean, you know, they both have a B in them, right? So your eyeballs may be tempted to say, oh, they look the same, but they're very different. And so, again, I guess as always, we're training our eyeballs to see the subtle differences and to attach meaning to the things that we see there, right? So it turns out that this is an addition reaction, and what we do have is pi electrons attacking a bromine, and then these electrons going off, and then you have bromide that leaves, right? So do you think molecular bromine is more likely to act as a nucleophile or an electrophile? And a good question is why? Why? All right, so let's look at this now. To promote EAS reactions between benzene and bromine, we saw in section 1 that iron is necessary. And here's the reason why. If you take bromine itself, it's not a super good electrophile. Because, got all these electrons here, right? However, if you complex it, I'm going to change colors. I really would love for you to hear these words I'm saying. They're not throwaway words. If you complex it with iron 3 bromide, if if you complex it with iron 3 bromide, which acts as a, can you see that this is acting as an electron pair acceptor? Which acts as a Lewis acid. Then what you have, you've got this complex here where this bromine now is electron poor, right? Because this one has a formal charge of +1, but it's really, you know, it's really sharing that plus charge with this other bromine over here. Okay, it has a formal charge of +1 because this has a formal charge of -1, right? And bromine's got two bromine has two bonds here. Now, here, Klein tells you, where am I here? Where's my marker? Here, Klein tells you that we are left with Br plus. This is not bromide. This is a Br plus, a bromine plus ion, cation, which is sort of like what we have up here, right? Can you see that in both cases, they're sort of equal, okay? In both cases, you can see that a nucleophile is going to attack here or here while these are getting kicked off, right? So they're really equivalent. And the reason I mention this is because, well, I want you to see that they're equivalent. You'll be better off if you do. And also, he shows both ways. And you're surely going to be wondering, why is he showing that? So let's look at this next one here. So, can you see why? The nucleophile, right? This is the nucleophile, is attacking, boom. Why is it attacking there and not here? Well, first of all, this has a filled octet already, right? And secondly, there really is, oops, escape, just me here. This plus charge here is really shared, right? Since there's a plus on here, it's drawing these electrons off. Since there's a plus on a bromine, which is an electronegative element, it's going to share it. So there's a partial positive over here, and bam, right? When those hit there, bam. The iron 3 bromide is released. Now it's got 4 bromines on it, okay? You see how iron 3 bromide is acting as a Lewis acid? Okay. Now, sometimes aluminum bromide is also used. So be expecting either AlBr3 or FeBr3. Be expecting either of those, okay? Or and a resonance stabilized carbocation. This is probably the most important thing we'll see all chapter. That's it right there. A resonance stabilized carbocation is formed. So now that that's gone, you see that we now have a bromine on there. There's the new bromine. That bromine is this bromine here. And these electrons, which were shared between this carbon and this carbon, no longer shared with this carbon, right? This carbon's lost it. Do not forget these formal charges. They are the key to making this easy for yourself. They're the key. All right, so let's move on now. First thing we get, and let me go back a step. Let me go back a slide. First thing we get is the preparation of the electrophile. We're making a good electrophile. This is not good electrophile. This is a good electrophile. So the first thing we're getting is the making of a good electrophile. That's what this is. Well, it says equilibrium here. Okay, I get that. All right, so we're making a good electrophile by complexing bromine with iron 3 bromide. And then, after we have a good electrophile, now this is a good electrophile, right? We need a good electrophile because our nucleophile is really pretty stable. So it's not really a super good nucleophile. But now that we have a good electrophile, the nucleophile comes in. Bam. All right. So far, making a good electrophile, and then the nucleophile hitting the good electrophile. All right. And then resonance stabilization. So this was what had been the electrophile, right? And so we have a carbocation, a secondary carbocation. It's actually resonance stabilized. So it's if that goes here, then we get this, right? You see, then this will become the plus, which we show over here. Then these pi electrons can resonate over here, in which case this one will be the carbocation. You see that? So they go back and forth. All right. So this is called the sigma complex. I'm not exactly sure why. It's probably Klein probably even tells us in the book, and I just never noticed it. Klein's not the only person who calls it a sigma complex, and I just never wondered why. So anyway, it's a sigma complex, and it's resonance stabilized. He says here in a recent conversation, I was a conversation with a student this morning, and I said this is a very common question. Draw the resonance hybrid. I haven't looked in my question bank yet from Wiley. I don't know that the question is in there, but every textbook asks it, draw the resonance hybrid. As I was talking to him, I could not find a picture of a resonance hybrid here in the textbook, and so I was a little bit saying, I don't know, maybe he's not going to ask it, but I'm going to ask it because it's important, and I'll say why it's important in a moment. But for now, draw the resonance hybrid. Pause the video and draw that. And then I'll show you. Okay, so as always, when we're drawing a resonance hybrid, we're going to go through every atom and every bond of all the hybrid contributors. One, two, and three, and we're going to average them out, right? So I see all three of these contributors, they all three have these things in common. Agreed? All three of them. Okay? Now, they all three have a hydrogen. They all three have a bromine atom here. They all three have a bond here. They all three have right? They all three have 6 carbon atoms. They all have hydrogens off of here. You don't have to have this drawn. I'm drawing that because it's not unusual for students to forget that there are hydrogens there, and you can't forget that. All right, now that we've got that, tell me, is this bond a single bond or a double bond? Do you see in all three cases it's a single bond? Single, single, and single? Okay, so that's a single bond. Is this bond a single bond or a double bond? Okay, so it looks like in 2 cases, it's a double, and in 1 case, it's a single. Do you see that? So I'm going to say it's partial. All right. Now, what about this carbon? It's neutral, neutral, plus. So this is going to be a partial. Crud, just a second here. Partial positive. Do you see that? It's neutral, neutral, and plus. Okay, now let's go to the next one. This one's neutral, neutral, and neutral. So there's no partial positive here. What about this bond? It's double, single, and single. So that looks like that's, all right? You see that? Now what about this carbon? It's neutral, plus, and neutral. So this is going to be partial positive. Okay, this bond is single, single, and double. Okay, what about this carbon? It's neutral, neutral, and neutral. So that does not get a partial positive. This bond is double, double, single. So that's okay. And this atom is neutral. No, do you see I'm just walking my way around this thing? I would love it if I could encourage some or maybe even all students to to be systematic in their approach. Okay, I'm not done, I guess. This one here is single, single, and single, right? So that's going to stay single. So this is the resonance hybrid. Okay, so why is this important? Oh, it's important because it tells us what are the most vulnerable places for attack. Okay, now right now we're going to have this pretty simple story here in the beginning of chapter 19, so we're not going to get much into it, but get used to drawing these resonance hybrids. They are the key. Okay, they're the key to what's going on. All right, now let's move on. There's your resonance hybrid. Hopefully that's good practice for you. Now it takes a lot of time, but all right. So the sigma complex, we're memorizing this, right? Because there's a couple things that could happen. One thing that could happen is we could have a nucleophile come and attack here, right? Or here, right? Because that was another location of, those were the three that were partially positive, right? Could attack all three of those places. Or we could have these electrons here on what's kind of like a bromide, right? If you see those electrons with this bromine, it's like a bromide. They could come and deprotonate, proton transfer. And that's exactly what happens. Okay? Why does that happen? Okay, let's see these two possibilities here. Oops, whoa. Okay, so possibility number one, or possibility number two. Why does two happen instead of one? Why? There's why. Because aromaticity is very stable. Aromaticity is very stable. Okay, so we want to restore that aromaticity. I shouldn't say we want to. These atoms have no real opinion. Okay, they have no real opinion, but it turns out that they're so stable that things have a tendency to fall into that condition. Okay. All right, so substitution, this is what I just answered a second ago. Substitution occurs rather than addition. Why? Well, here's the addition. This was that pathway number one that I referred to in the previous slide. That would go there. And here's pathway number two, substitution, pathway number two. And this is the reason why. Look at this, is a huge energetic benefit. Look at that, you see that? Big difference here. I mean, we don't have this quantified, so you can't see how big it is, but I'm you know, if you can appreciate from our last chapter how important aromaticity is, then perhaps that can help you appreciate. Either way, another thing we can do, of course, is we could simply just memorize it. You know, this is called electrophilic aromatic substitution. Why we're talking about this right now is to explain why it happens, but in the end, it happens, EAS. Okay? All right, now chlorine can also be used. If chlorine is used, we don't use FeCl3 that I know of. I do know we use, I'm going to feel silly if the next slide has it, but this is the primary catalyst for chlorination. All right, it happens exactly the same way. So draw now. I'm going to ask you to pause the video. This mechanism is in your book. I think it's 895. I don't remember now. 885. No, I don't remember where this is. It's in chapter 19, of course, but I don't remember where this mechanism is. But draw the EAS mechanism. Try to do it without the book, and then after you've tried, just go back through these slides and try to mimic what is happening. It's just like iron 3 bromide. Do it with aluminum chloride, and then go check your answer with the book. Okay, So fluorination is generally too violent to be practical because it's too reactive, and iodination is generally slow with low yields. And so we'll see later how to get a fluorine on there or a bromine, fluorine or an iodine. But for now, we've got these are what we're learning for this chapter.